All right, guys, so you have questions about the homework. So that's problem 1. So let's look at problem 3, which basically is this one over here. So the problem statement states that a mass M is suspended from a spring of stiffness 4,000 and is subjected to a harmonic force having an amplitude of 100 newtons and a frequency of 5 hertz. The amplitude of the force motion of the mass is observed to be 20 millimeters. Find the value of M. Okay? So let's see. If I have to do this problem, what would I do? Not good. All right, so problem 3. So what I would do is this. So mass is suspended from a spring of stiffness 4,000 and is subjected to a harmonic force. All right, so basically you can do it up and down, it doesn't matter. Let me just do it up. So there's a mass K. Subject to harmonic force. Now this is subjected to an harmonic force here, F of T. Subjected to harmonic force having amplitude of, so this would be F sub naught EI capital omega T, where basically I'm telling you that S sub naught is 100 newtons and that the force frequency is 5 hertz. Okay? Okay, so there's no damping. I was just waiting to see if it was damping, but there's no damping. And they tell you the amplitude of the force motion of the mass is observed to be 20 millimeters. Okay, so X max. So let's say here X max equal to 20 millimeter. And basically, if I have to put here a damper, there is no damping, no? Okay. All right, so what I would write over here is that the general form of the equation of motion for the above system, so equation of motion, you don't need to derive it. Okay, you have done it too many times, will be our which form? Mx double dot plus kx would be equal to f of t, no? Okay, now I will say the solution to that equation just is obtained by what? So assume x of t would be equal to x sub naught, which is actually, okay, and now comes the important part. You need to assume the solution being function of the force frequency, 5 hertz. This is not the natural frequency, no? Okay, this is the force frequency of this one, all right? So, and you say, substituting into the equation of motion, all right? You don't need to say all the process, you probably go to the notes, you will say that x of t is equal to x sub naught, and let's look for the solution. So here, why I don't have access to my drive? Resume recording. Okay, so we can say from page 63 on the class notes. So it's equal to x sub naught E I omega t minus phi, where x sub naught is equal to f sub naught over m, one omega n square, one minus capital omega over omega n. I just put omega square, everything square, plus 4c square, capital omega over omega square, and this is the square root of everything. Okay, but here we don't have, let's see what we need over here, right? Okay, so in this problem, so for this problem, there is no damping. So what does that mean? That this time is zero, no? Okay, so we can say that in that case, x sub naught would be equal to f sub naught over m, 1 divided by, okay, this should be omega n squared. And then we should just have here the value of the square root of 1 minus capital omega over omega n square, everything squared. All right, so let me go back to the problem statement. A mass is suspended from the spring. The amplitude of the first motion of the mass is observed to be 20 millimeters. Find the value of m. So we need to find the mass. Okay, so let me think for 1 second. Okay, so in this time I forgot to put that the stiffness, K here, is 4,000 Newton meter, and this here they never say this is a maximum, so they just say this is X. All right. Okay. So basically, what does that mean? That the response X of t is given by what? Is given by this, so naught over m, 1 over omega n square of 1 minus omega n square. And it should be now the E I omega t minus 1. So this is the value of the response, okay? All right, so over here, I think what we're going to do is that now we're going to know that this, if this is 20 millimeters, let's see what could happen over here, okay? So let's come over here. So this is 20 millimeters at a sense function of time. Somebody mentioned, if you want, we can solve it with x of 0. Let's say this is, we know this is x of 0. All right. All right, so I think what we need to do at the end with this problem is this. So basically, if you want, we're going to have x sub 0, which is the 20 millimeters should be equal to F sum naught over M of 1 divided by omega n square. And now, here we have the square root, but this is squared, so we should be able to take it out, no? So here we need to be careful because I think this is going to be, needs to be the absolute value of 1 minus over square. Omega n square, we know is k over m. All right, so here what I would do is actually go to Maple. So let me pause it a second. So we don't waste time. So it's over here. So let's first look at what should be Q omega. That way we resolve any doubt. So this is 5 hertz. Okay, so this should be just multiplied by 2 pi. I don't know, I was thinking about revolution. So this should be 5 times 2 pi. So it should be 10 pi radians per second. Okay? So let's go back to the Maple page. So basically, guys, probably this by hand can be a little bit tedious to do. But one thing I want to point out here is what I pointed out before is that this absolute value, so if you solve for this absolute value, what do you need to do? Once you solve this equation here, all right, you move, let's say, you move all the terms that are on this side, you leave this one alone on one side, all right? And then what you need to solve is plus minus the other side. So what I'm trying to say is basically is that because of this absolute value, all right, so you solve one equation, so this is math, if you want, to say if you solve this, a plus b, you need to do, this will be equal to plus minus c. So you need to solve twice. One for plus c and one for minus c. Okay, so this will give you 2 solutions. So those 2 solutions are the one that the Maple code is giving us over here. So obviously one is a negative, which cannot be, and the other one is 9.1189 kilograms. Okay, so let's just say here, why do it in green? Using Maple to solve the problem. I see here C attached document. Okay, I will print it and scan it, and I can put it if you want it. We get that M equal to 9.1189 kilograms, because the other answer makes no sense, no? So I'm guessing here, guys, if you got a different answer, it's maybe because you only solved for one of the roots, and maybe was the other one. Okay. I think that might be the only error I think you may have done. And to solve this by hand actually should not be that bad, but it might be easier. Yeah, I don't know what might be easier. It might be a bit tedious to do that by hand, no? Okay. So on the homework, if you want, you can use Maple. Just make sure you attach your Maple input file. Okay, just like we did now. All right, so now let's look at problem 1 out of the homework. So this is an air compressor of mass 100 kilograms is mounted on an elastic foundation. It has been observed that when harmonic force of amplitude 100 newtons is applied to the compressor, the maximum steady state displacement is 5 millimeters, occur at a frequency of 300 RPM. This is why I have in my memory RPM, because remember reading RPMs. Determine the equivalent stiffness and damping. Okay, so basically, this is kind of look like the other problem, but this time the damping will not be zero, no? So if we do the figure, looks kind of similar figure as the one we did before. So we have K, C, M. The force vibration. And now what we have? M equal to 100 kilograms. When harmonic force, so F equal, so would be F sub naught equal to whatever, 100 newtons is applied to the compressor. The maximum steady displacement, so X max this time, which probably ended up being X sub naught as well, will be 5 millimeters. Occur at a frequency. Okay, so this is important here. What does the term maximum here implies? What does that imply? When is the maximum amplitude going to happen? No, it's going to happen at resonance. What was resonance? So let's see if we have the figure here. And this is the kind of stuff we're looking at the other day. So let's see if I have a figure here. What is resonance? Resonance happens here, no? Yeah, you see here it would be everything goes to zero. So then what does that mean? What happens at 1? Is that is at the point where the normal frequency is equal to the force frequency. Yeah? Okay. So that implies what? So in this case, we could say that because it's maximum, and also at maximum deformation, that happens at resonance, which means what? That the natural frequency is equal to the force frequency. Okay? Occur at a frequency, and we know here that, so let's say capital omega, or omega sub n, is equal to 300 RPM. So we do the transformation, that should be what? 1 revolution should be 2 pi. And then so this is per minute, and 1 minute here should be 60 seconds, no? So this will give us what? So this should give you whatever. This is 5. So 5, 10 pi? 10 pi radians per second, no? So as before, 10 pi radians per second. Okay, and over here, what we need to do is find K and C. Okay, so I think we need the same equations as before. All right, so the equation of motion for the above system is of the form again mx double dot plus cx dot plus kx equal to f of t. All right. If we assume solution, x of t equal x sub naught e I omega t, and substitute into the equation of motion, what do we get? The same equation that I had before, x of t equal to x sub naught e I omega t minus phi, where x sub naught was that long expression that we had before, f sub naught over m. I think we had the, yeah, here it is. I have it right in front of me, of omega sub n square. Then we have the square root of 1 minus omega over omega n square, for this square, plus 4 c square omega over omega n square. And this should be the square root. And on top we have 1. Okay, so it looks like over here, the easiest things to do might be able just to solve first for the damping, no? Because we can say at resonance, what we have, those two are equal. All right, so what does that mean? So if we use x sub naught, so x sub naught, let's say, would be x max. And this should be equal to what? F sub naught over m. Now, this term will be 0 because capital omega is equal to lowercase omega, no? So this term is 0, so we end up with 1 over omega n square of the square root of 4 c square. I think that's it. But now we need to be careful because what is omega sub n? Omega sub n is also a function. Well, we need to be careful here because this is a damp, no? I looked at this problem the other day, so okay, let me pause this for a second. Okay, so guys, here this is the 300 RPM, so the one we calculate here to be the 10 pi radians per second is not really the natural frequency because it is damping, so this should be the damp frequency. All right, but this is what happened at resonance because it is damping. So the omega sub d is equal to, this is the expression which is k over m of 1 minus the damping. So here we got one first equation. Let's see, we have equation 1 here that says that k over m of 1 minus the damping ratio is equal to 10 pi. So here we have m is known, damping is unknown, and k is unknown, which is what we need to find. K over c, this is related to damping. So one equation, two unknowns, we need to find an additional equation. we can probably use the fact of the maximum deformation to be 5 millimeters, substitute over here, and find a new equation. Okay? So we can go now, let's say, so it should be our equation 1. And now we can say, to find the second equation, we use the expression x sub naught will be equal to x max and resonance. And this is equal to f sub naught over m of 1 and now this should be really the omega sub n, because that was we had on the expression, no? Yeah, that one, the damping is taken into consideration there. So it should be omega sub n square of 1 minus, so this term again should be equal. So this term will be equal to 0, is what we did at the beginning. We already did that equation here. Sorry for that, I'm just writing, but we already did it over here, no? Okay. Just redo it, doesn't matter. Square plus 4c capital omega over omega n square, and this should be 1/2. So our resonance I don't know if it's going to keep the same thing here, because this omega, is that omega or omega n of the equation? Do you remember, guys, or not, from the equation we wrote initially? From the one on the class notes. Omega n, okay, so then it's omega n, so resonance. I mean, if the damping is very small, it's very for the same. So we say that resonance we have, this is equal to f sub naught. So we have just copy from before, equal to f sub naught over m of 1. So this should be here 0 of omega n square, and then you're gonna have, so this will be 0, we're gonna have 4 c square 1/2, so this gives you x sub naught equal to f sub naught divided by m times 1 over k over m. Okay, so over here, let's say our equation 2 should be x sub naught minus f sub naught over m 1 divided by k over m 2 of this one. Okay, let's go to Maple and let's try to solve this problem. All right, so now we have these two systems of equations that we need to solve. So this is the, if we solve these two equations, this is what we have. So let me just write it over here. So we can write down over here again, using Maple. It is found that, let's see, K is equal to 99699 Newton per meters, and that Xc is equal to 0.1003. Okay, so in this problem, again, I'm going to do it this way, but we don't want to get exactly the same thing. They don't ask us for C, they ask us for C. Okay, so the relation that we have for C was what? Is that by definition, C is C over the critical damping ratio, and the critical damping ratio is equal to 2m omega sub n. So this is equal to C over 2m K over m, which will give you that the damping value C will be equal to 2m square root of K over m times C. All right, so if I substitute into this MATLAB file, then we give us C equal to 2 times m times S square RT of K divided by m times C. All right, and here he's not going to do it because he's not going to recognize them. In here we should put another one, saying for example that this will be the damping, and this will be the damping. This. So we get 633.4093. So it should give you C equal to 633.409. Okay, so this is our problem one. We have two problems one now, so it should be, let's see, D1. Okay. So now, let me go back to the problem, because this is the solution now in the solution manual. Now, if in this equation, instead of using omega sub n, we use omega sub d. Okay, which omega sub d is what? Is omega sub n 1 minus xc squared. Okay, so we do exactly the same thing. So we use, instead of the omega sub n, the omega sub d. So this is what is done in this question here. You see that this is the omega, capital Omega. This is the omega, this is the omega, and the omega is the damp. Right, so it should be not minus 2, but minus just c squared, no? So let's see what happened. Then, oops. That's the good thing about that, is that you do an error and you don't have to recalculate everything. So you can do very quick. In our case, what do we say? We say this one will be equal, correct? So this was 1 and this was 1, no? Okay? So we get this. So now we're going to get probably, okay, so we get, so you see actually, this is very close, so it should be C is equal to this. Why do we get two values? Because it's a square, no? Okay, I don't know what happened here. That's not what I wanted to do, but all right, so this should give you this. So actually, if we use the correct equation,
What's the difference?
the what?
What's the difference?
No, but this is the one I did before. What happened is that I think they have a 2 here. I think that's wrong, okay? We check. So if you use the 2, we get exactly as I have on the solution manual, which is the 2 times. So we need to check that equation, but I think we check it. If we do this, you see here the damping ratio should be a little bit smaller. So the damping ratio is 1.0185. I mean, those changes are so small that, I mean, we don't really care, no? I mean, personally, I don't care that much. We have this. This will give you the damping. And others will be the stiffness, which is what they have on the solution over here, the 633 and the 107, no? But I think the whole problem comes to this equation. This is, I mean, we need to double check, but I think we did the previous one without the 2 here. Correct? Okay, so even you see that the solution manual might be not correct, no? I mean, the difference is small. So we do that. So use, I'm going to give you this file, use whatever you want. But I think it's this one, no? From what we checked. We do, let me go back again because I need to reinitiate. So this should be, all right, 17167 705. So 632 instead of 633, and this one give you 6. I mean, they are very close, no?